Yes.
Is there a way to get access to some of these presentations after the fact?
I expect so. There should be a website that's going to have it all.
Because I looked for last year's and I
You can go
couldn't
online
find it.
and there's an agenda, and I think that there's probably something.
So it's a whole different organization this year, with having this be separate. I'll see to it that happens in some fashion.
There's one of the last lectures I was in here earlier that I didn't see the guy who gave that, and I really like to know more about that.
Right. Yeah. There's also some posters. That some people giving talks will also have posters where you can quiz them further on what's going on.
That's at 5, right?
That's at 5 o'clock.
I think you can always look on the agenda and see just
Really?
anyone's name on it, and then look them up in the UCLA directory in
Yeah,
email.
or Google them, and often students' talks come straight up there also, since many of them are looking for jobs.
Yes.
Okay, well, I guess I better follow orders and get this session going. I'm Greg Potty, and this is the Advances in Sensor Network session. And our first speaker is Lucas Wanner from, actually, which group are you in? That's okay, so Professor Srivastava's group.
Good afternoon, everyone. My name is Lucas Wanner, and I'm in the Network and Embedded Systems Lab. But this is a joint work between Nestle and the NAMCA Lab, so under invitation of Professor Gupta and Professor Srivastava. And I'll be talking about variability-aware testing for sensor networks. So here's an outline for my talk. I'll first talk about variability in contemporary embedded systems hardware. Then I'll talk about tasking and duty cycling in sensor networks. When you have this variability, I'll talk about duty cycle scheduling methods. I'll talk about our software architecture, show results, and conclude. So let's start with variability in contemporary embedded sensor hardware. So first, what is this variability problem? The variability problem comes up when, very simply, when you have nominally identical parts, but different characteristics. So these characteristics could be a maximum frequency for which you can operate that part, error characteristics, and the focus of this work, power variation. And so, just a little bit about causes of variability. First and foremost, is difficulties in semiconductor manufacturing when you scale physical dimensions. So when you scale physical dimensions enough, what you see in your design is not what you get in your fabrication. Also, vendor differences. If you source your parts from multiple vendors, you get differences there. Aging because of temporal stress, for example, due to NBTI. And finally, ambient conditions. So especially in sensor networks, you usually deploy them on the field with wide variations in temperature. So this is important. This is especially important for us. So if we look at ITRS projections for variability, this plot here shows here, and on the y-axis, bar chart variation in total system power and in static or sleep power. So you can see that this is a problem that already exists now and is expected to get worse. Okay? But instead of only looking at projections, we start with the question of what is the extent of both active and sleep power variation in hardware that we can buy now. So in contemporary embedded sensor hardware. So we looked at the question by measuring both active and sleep power for Cortex M3 CPU. This is an Atmel Sim3U part, or actually 10 parts that are identical. And here on this plot, I'm showing active power across these 10 parts. So you can see that measured active power has a range from about 4.8 to around 5 milliamps. So there is some variation, but if you look at the extremes, there isn't a whole lot of variation. So about 5% variation across these 10 parts. Now, when you look at the power for these 10 parts across temperature, you see that variation increases quite a bit. So this is again our 10 different parts, measured power across a range from -50 to 150 degrees Celsius. So put all the parts in a temperature chamber, measured power for inactive mode. So again, if you look at the extremes, for any one part, we see a minimum variation of around 28%. across this 200 degrees range. Maximum variation again for a single part around 38%, and across the board from best case power at lower temperature to worst case power at higher temperature, you see around 44% variation. So once you put temperature into the equation, you also see more significant variation in active power. Now if you look at sleep power, this is what we can expect from the data sheet. All parts would be around 15 microamp in this case. When this is again at room temperature, when we measure power for these 10 parts, you see a huge variation in actual measured power, from around 9 microamps to almost 80 microamps in this case. This is all at room temperature. So if you look at the extremes, now in sleep power, in measured sleep power, we see around a 9x variation across the 10 parts. If we look again across temperature, this is a much smaller temperature range from around 20 to 60 degrees Celsius. We also see a lot more variation in this one. So in the best case, around 30% variation for this 40 degrees Celsius range. In the worst case, for a single part, around 4x variation, and across the board from again, best case to worst case, around a 14x variation. So then, knowing that, what should we do about tasking and duty cycling our wireless sensors? So first of all, let's talk about how these sensors are typically used. So usually in sensor networks, you'll have a system that is heavily duty cycled. Every once in a while, the system will wake up, will get a sample from a sensor, will process that sample, will send something through the radio and so on, and will then go back to sleep for a larger period. So this alternates throughout the lifetime of the system. So a small active period, large sleep period. And duty cycle is simply the active period over the activation period. So when we're designing the systems, we typically aim for higher duty cycle, because higher duty cycle typically translates into better quality of sensing. So if you have either more computation time, more active period, or a smaller sleep period, you typically get better probability of detecting an event. You simply get more data samples. This is important in some applications. You get better classification accuracy and so on. So then, if we're trying to determine our duty cycle, we're essentially trying to determine the active period and the sleep period as a function of active power, sleep power, how much energy we have, is the size of our battery, and for how long should our system last, the lifetime of the system. So if we're determining this function, we typically go to the data sheet, look at active power, look at sleep power, we know the size of our battery, we know the lifetime that we want, we're done. But as I showed you, you have this increasing effect of power variation. So once this comes into play, we can simply plug those numbers in. They won't be representative of what we'll actually find. So the question that we're trying to answer is then, how can we adapt duty cycle when active and sleep power vary with both instance and temperature? So next then, I'll talk about duty cycle scaling. I'll talk about our choices when we're trying to duty cycle the system. The first choice is we can simply use the data sheet. So this is the yellow line there, it's sleep power. The green bars are measured power. So if we use the data sheet value for sleep power when determining our duty cycle here, one or two things will happen. If our actual power is lower than the data sheet power, we will meet the lifetime that we want, but we'll leave out energy in it. That is, we'll leave battery unused that we could use to improve our application of sensing power. And the worst case is actually when our actual power is higher than our design power, the spec power. So in these cases, we won't be able to meet the lifetime. So our system will die before its lifetime is completed. So that's our first choice. Our second choice would be to get a better value for our spec. So instead of simply looking at the data sheet, let's try to look at the worst case power for all our boards or for all our processors across the operating temperature that we do. So say our maximum temperature is 45 degrees, we look at the worst case power at that point and use that as our sleep and likewise active power. So what will happen here is that unless you're always operating with that worst case board at 45 degrees Celsius, you, of course, will meet your lifetime, but all of your nodes are going to leave out energy. So you're not using all the energy that you can use to improve your application quality. So what we really want is to maximize active time, maximize the number of samples that you can get, maximize our detection probability, and so on. But we got to do that subject to our required lifetime and how much energy. We already have active and sleep power characterized as a function of instance and temperature. So if we went one step further, instead of knowing something about temperature in the future, what we could do is say if we could know temperature as a function of time, we could translate that temperature curve into a power curve. And so we just so we determine our power as a function of time, and we say we use a linear program to maximize active time, subject to energy and lifetime, with our known future power curve. But of course, that's not really feasible. We don't have a crystal ball to find what temperature will be in the future, but it turns out we don't really need it. All we need to know is temperature distribution. So throughout the lifetime of the application, what will be your expected temperature distribution. And this is much easier to characterize, it's easier to learn. And so instead of determining duty cycle as a function of time, we determine duty cycle as a function of instance and temperature. But we can go one step further. And instead of having a variable duty cycle, we have a duty cycle that's variability aware, but is constant for any given instance. So essentially what we're doing in this case is taking a weighted mean of power across some temperature profile for one instance. So in this case, we'll determine the cycle for each instance, but this duty cycle will be constant for any given temperature profile. And it turns out that when the difference between active and sleep power is relatively constant across temperature, this method gives the optimum duty cycle, and this is true for our centrifuge flash. So next, let's look at how a software architecture can exploit this. So this is how a duty cycle is typically implemented in really any embedded operating system, but in this particular case in Timex, which is a system widely used in systems. You have a timer associated with each task. When the timer fires, you have some computation. You do something that's your activity. So duty cycle for your task is going to be your active time over your period. So if you want to adapt to the cycle, you've got to change either the computation time, the active time, or the period with which that task is activated. So what we did is we extended this idea to have tasks with both adaptable periods and adaptable number of iterations. So a task with adaptable period always does the same thing, always has the same computation time, but the period with which that task is activated is elastic. We go from a minimum to a maximum. And likewise, we have tests with a fixed period, but with an adaptable number of iterations. That is, each time the period is up, we're going to call that task I times, and I varies from a minimum to a maximum. So what the system will do then is activate the task at the maximum allowable. So we have our tests with adaptable periods, we have our tests with adaptable number of iterations for each period, and we have our tests that are not adaptable. So our tests with adaptable periods and adaptable iterations will turn into simply adaptable tests. And the duty cycle kernel scheduler, based on our known temperature versus power curve for each instance, will then determine the allowable duty cycle and adapt both the period and the number of iterations for these tests automatically. Okay. So let's look at our results. This is comparing, this plot here is comparing our three schemes. One is duty cycle based on data sheet, the other one is duty cycle based on worst case power, and third one is our variability. This is for one of those 10 instances for one specific temperature curve. So what's happening here? We have a curve here on the bottom, very close to zero. That's our duty cycle based on the worst case. So what's happening here is that we have a duty cycle that's able to use the lifetime but it's very low. So on the middle here we have a variability-aware duty cycle. That's the maximum duty cycle that is able to meet the lifetime for that one instance. And the third curve, which is the one that starts high and then drops to zero, that's our duty cycle based on data sheet. So when we base our duty cycle on data sheet for this one instance, our actual power is higher than data sheet power. So what happens is we start with a high duty cycle. At some point in the lifetime, the battery is exhausted. It drops to zero. So this is for one of the 10 boards. If you look for all the other 9 boards, we see an improvement over the worst case, a variability-aware over worst case that ranges from about 3x to almost 30x, depending on how worse your power is than expected. And on average, a 22x improvement over these 9 boards. This improvement is because when you base your duty cycle on worst case power, you're leaving out most of the battery untapped. So this is how much battery you have left if you use duty cycle based on worst case. So something from about 10% to almost 90%. And on average, for this one scenario here, you're leaving out 63% of battery untapped at the end of the lifetime of one. If we look at the flip side, if we're looking at duty cycle based on data sheet, here we have two cases where P2 and P10 have power that is actually lower than the data sheet, so those have the lifetime as well. But for the other 8 boards, we weren't able to meet the lifetime. And on average for the 10 processors, are able for 55 days for 1 year time. So what does that mean in terms of application volume? All those numbers that I showed you before in terms of raw active time, so raw number of samples. If you translate this into an application, we're going to get the 3 curves. And this is an application that's doing localization using maximum likelihood estimation. This is a 10 by 10 meter grid, and we have our 10 nodes as I described before, and we have 3 curves again. So the curve of the highest error is the one based on worst case data sheet. The one in the middle is the optimal duty cycle, the variability-aware duty cycle, which is about 50% better than the worst case. So a 22x improvement in active time translates into about 50% gain in provision quality. And finally, the bottom curve, which is the most interesting one, is again the duty cycle based on data sheet. So you start out with a high duty cycle, very low error, but as your lifetime progresses, nodes start to die, up to a point where your results are worse than random nodes. So as your nodes die, your results get progressively worse. As I said, this was all for one particular application scenario, one particular temperature scenario, and that was in Death Valley, California. So I wanted to stress out the benefits of the trades-off of these schemes. So I picked a temperature profile which first of all has very high temperature, and second has a lot of temperature variation, both across the year and for any given day. So you see that's kind of the right part of this one. And if you go towards the left, towards milder climates, up to where you have constant temperature, your benefits sort of decrease as you go along, up to a point where you get your constant temperature. You still get benefits, but you're not getting benefits because of temperature variation, you're getting benefits, because of bar-to-bar variation. So you still get benefits, but not as much. So, in conclusion, we're seeing the effects of growing variability. So we need a software stack that adapts your hardware as measured, as opposed to your hardware that's designed or as specified. We talked about duty cycle with sensing systems, where if you take the conservative spec, if you take the worst case power, you'll end up with untapped energy. And if you go with an optimistic specification, that is, if you go with the duty cycle, you'll end up with unmet lifetime requirements. We talked about a variability-aware duty cycle scheduler that optimizes duty cycle with lifetime constraints. We talked about how this is implemented in TinyWet, so for duty software architecture. And across 100 locations for each region, we ran 100 different temperature profiles. We saw an average 7x improvement over the consensus spec. In terms of ongoing work, we're looking into alternative methods for exposing this variation to the higher software layers, not only based on cheap variation monitoring strategies. For this work, everything was pre-characterized, and so we're looking at learning these curves as we go along. The implications of this for hardware design. You can see a little more about this at our NSF Variability Solution website and variability.org. And that's it. Thank you, and I'll take any questions.
Questions?
I guess in this case, you physically pre-measured the characteristics of each device and then programmed that to each device. So
Right.
it's kind of labor intensive.
Well, some of these tests already go into the manufacturing process. We just don't record that information. So yes, it would be an extra cost, but it's not something that sounds too unreasonable.
Yes.
Have you considered switching back and forth between what you have presented versus that for meeting sensor networks objectives from time to time? That is, in one of the slide that you show, the error initially, if you don't use your method, was much lower until a certain time, which might be what's required for certain tasks, applications. Have you considered switching it back and forth
In this
to meet
case,
both
our
objectives?
our hard constraint was lifetime. So you could play the opposite game and go for aim for some quality and then see how long our nose lasts. It's kind of the same problem, just a slightly different parameters. But in our case, we always fix the lifetime. The lifetime was the one requirement. But you could do the same with aim for a quality and see how long your sensor network lasts.
Well, I think it's switching it both ways. So you aim for some quality, and if you meet that objective, then you switch back to maximizing energy, and then you switch back to meeting the objective of sensing. So over time, the period of this.
Right.
That-
Once you meet that quality, you don't have to improve it.
That's right.
You could do that. That's a good suggestion.
Okay, let's thank our speaker again. And up next,